Hello everyone. My name is Michał Dominiak. I'm a student at Wrocław University of Technology, that's in Poland. I also work at Nokia Networks. And this is going to be a talk about functional programming in a way. Okay, so we are going to start with a short introduction that will actually tell us what I'm going to talk about. And then we will meet some of the ideas that govern functional programming. So purity of functions, functional data structures, avoiding shared state, mutable shared state, of course, composability, and kind of laziness, trying to design your interfaces for success, and not for the exceptional cases. And of course, we will talk about writing generic code. And noticing patterns in the code we write and creating abstractions from that. And then at 8:30 there will be a session about functors and monads. And I'd like to invite you for it. Okay. So functional programming is a paradigm. So a set of ideas and techniques. And the techniques are not as important as the ideas that are below them. And techniques are just means to express the idea, to implement it. And ideas are applicable in almost every programming language, especially where in C++, which is, as we all know, multi-paradigm and should take the best parts of every paradigm that is usable in it. So we will talk mainly about ideas and not as much about techniques, so the implementation of those ideas. What I mean about code, what I mean by code design, it's all the steps from the initial idea about an application or a library to the implementation deep below, including the implementation of specific functions in the interfaces. Okay. So I'm going to talk about some guidelines about how you can design and write code to kind of follow the functional programming paradigm. And I would like to give some explanation for choices you have, because you cannot make a decision about design, about the way you are writing code without knowing the possible choices. This is not a talk that consists of do and do not. So we had talks like that this week already, so this is not another one. And this is not a talk that religiously follows a paradigm, the paradigm. So there's that. Following anything religiously without any kind of reasoning usually makes no sense. Okay, so the first of the ideas is purity of functions. What does it mean for a function to be pure? A pure function is a function that does not cause side effects, and that for every that when called with the same set of arguments, it always returns the same value. And it's the value that matters, not the state of the object that is passed. Okay, so it's easier to reason about them. We don't have to think about implicit inputs for a function when it's pure, when we know it's pure. And as long as the function is named correctly, we can usually, from the set of arguments from the name, understand what is happening below in the implementation without even seeing it. They can be optimized better. So the compiler, if it knows that a function is pure, it can optimize it more aggressively and make, for example, a single one call to a function instead of multiple ones as are written in code. And thanks to the definition, they do not cause side effects. They are not affected by side effects of other functions. They are thread safe, which is more and more important as time passes due to how processors are being built these days. Okay, so there was a proposal in 2013 by Walter Brown. I am not sure what is the status of that proposal. And it proposes an attribute that says you cannot throw an exception. If you throw an exception, your function is not pure. And I don't exactly agree with this approach. I believe that in this case, if an exception is always thrown for a given set of arguments, the function is still pure. So my argument kind of follows the fact that exceptions are monadic, which I invite you to listen about in the next talk. And so in C++ we have the proposed attribute, kind of, I mean the exceptions part. We have const-expr. Const-expr functions, if they are used in a constant expression context, must be pure, otherwise your code will not compile. So that is one of the ways we kind of have pure functions in C++ right now. Const-expr also follows the idea that throwing an exception makes a function not pure. And there's a GNU extension for this, attribute pure. It's supported by GCC, it's supported by Clang, and it's supported by ICC. So it's quite widely available. And one last point here is that the intuition would be that mathematical functions should be pure. But one frequently overlooked property of floating point numbers and their implementation, as it's usually executed in modern hardware, one overlooked thing is that they are not exactly mathematically correct. So floating point functions will often not be pure in the general sense, especially since there are hardware registers. For example, controlling how a floating point is rounded, which will cause floating point operations sometimes give us different return value for the same input arguments. Okay, so we would like our functions to be pure because it's easier to reason about them. The compiler in ideal world understands them better, can do smarter things with them. But usually when we have a data structure, at some point we would like to change it, to have a different structure for whatever reason. We cannot do that in pure way with normal data structures, the ones we know usually. Immutability helps, of course, in this case. So immutable types, which we can in C++, probably the best way to get them in C++ is declare a type with all of its member const. Of course, this may be walked around with constcast, which causes undefined behavior, which we don't care about because it's undefined. And this way we have a type which cannot be changed in any way. as long as the code we are calling is safe or tested. And const member functions cannot be really guaranteed to be pure, even if we are considering only purity in the scope of an object. So just seeing that a member function is constant doesn't tell us much about it. We can mark members as mutable, which means we can change them even when we are operating on a const object. This, of course, causes such types to be incompatible with, for example, standard containers, but they can still be found in the wild of the C++ world. So, but how is that really useful? Because if all the member fields are marked const, we cannot do some operations with them. For example, when we have them in a vector, we cannot call erase, because erase moves or copies, but moves some objects around, and you cannot move into a object that is composed only of constant members. So we need something else. We need data structures that are designed to operate on such types. And this is usually called functional data structures. And usually the only case where they make sense is node-based containers, because we can share ownership of individual nodes between multiple data structures. I'm consciously not touching the topic of performance caused by cache misses, whatever. This is not in the scope of this talk. So nodes can be shared, and we can use less memory than we would use if the nodes were individually owned by each instance of a data structure. And the functions that change something about the data structure don't really make a change in it. Instead, we return a new instance of the data structure, and by the consequence, those functions are pure. So even if we are constructing multiple identical copies of an instance of a data structure, the compiler can be smart about it and can figure out that we are really creating an identical thing multiple times, can optimize it. And it's also automatically thread safe. The data is immutable. We can't possibly run into data races by definition. So when talking about purity and functional data structures, we want to avoid getting into situations where we share mutable data. And we want to avoid doing synchronization manually. We would like to have that by default automatically. And this is possible with functional data structures. Nobody likes global variables except when they are constant. Constant global variables are pretty useful sometimes and are free of most of the shortcomings of mutable global variables. So ideally, you would like to design most of your functions to be pure, to operate on inputs, do something inside, return a value. And that also excludes functions that mutate an object they are called on. And yes, so when you are sharing data, try to share immutable data. Do not force anything. Sometimes sharing mutable data is the correct solution due to various circumstances. And sometimes even implementing synchronization manually will yield better results than using immutable data structures. This can be, for example, caused by a data type that has identity, so refers in a way to itself. So the particular address of the object is important. You cannot really have that with not mutating algorithms or functions, because the object that will be returned will be a new one and will not be related in any way to the old one. And also, when you're writing an interface which is supposed to do something, for example, you have an input, a string or a file, and you want to parse it. In general, you want to create a function that will do just that, so we'll parse the file, parse the text. Instead of creating a parser, so an object that will, by manipulating its internal state, parse the data. You are parsing, so you want to parse and not create a parser and do additional things with it. Okay, so the next important point is composability. Functions that follow value semantics, so take values as inputs, return values, are composable. Pure functions generally follow value semantics. A lot of mutating functions, but not all of them, of course, follow reference semantics. So, for example, standard sort takes de facto two references into the same object and mutates the object based on those references. That's not composable. You cannot return a container and pass it to standard sort and expect it to do the right thing, because you need two references into that container. So you have to save it, take those two references, pass it to a function. Yeah. So this was, of course, noticed. I guess not many people really like calling functions with iterators. There was boost range. There is a proposal for ranges that would kind of operate in this way, but not entirely, not always. Some of the algorithms are still not pure, still just mutate a range instead of taking it by value and returning a new value. And which one feels better, the first one or the first piece of code or the second one? Because I personally much more prefer the first one. It's not really. I'm not really a fan of having to create a copy and then mutating it. I would like to have that encapsulated into a single function. That is my preferred interface because it's composable, unlike the second one. So when your algorithms or your functions are composable, you have a way to impose laziness onto your code. You don't have to, when you have an algorithm, for example, sort, you do not have to return a container. You can return an object that represents a computation. Other algorithms can be made aware of that kind of an object and can do something smarter about it. Okay, so mutating is fine, and breaking the rules locally, even if we set them ourselves, is fine. It's the same case as is with type invariants. As long as the invalid state doesn't escape a local scope, so no one outside of us can see the invalid state, we are okay. So we can take a function, we can take a value, mutate it locally, return a new value, and no one will see that we mutated it. So we are pure, even though our implementation uses impure functions. And yeah, mutating algorithms are not lazy. And a simple example, if we have a range and we first sort it, then we filter some elements out or some elements in, we sorted too many elements. We sorted the parts of the range that we do not care about, which we are throwing away right after that. And if we first filter, then sort, that is all right. But if our algorithms are lazy, they may have a chance to figure this out for us. And we could not care about the particular order of operations or the particular way we describe an idea, we describe a sequence of computations, and the code can figure out the correct one for us. Okay, so we want to write generic code. And we want to know what we are doing. We want to do that for a reason, not accidentally. And C++ has this weird thing where different elements of the library, different features, are designed like they look like they've been designed to be incompatible with themselves by design. For example, we can get a pointer from shared pointer, a row pointer, and we can get a value from a future. But in one case we get a pointer, in the other case we get a value. And for optional, we can also get the value, but the function is not called get, it's called value. As like if somebody wanted to make them incompatible for whatever reason. The same goes for operator, dereference operator. And I think that this may follow from the fact that some pieces of code that we are still using were kind of over-engineered, over-generalized. And we look at them and we have a feeling, no, I will not do that. I will not go that way. I will consciously not go that way, and I will not generalize my code. That is not a really good way to write code. Maybe some people are just afraid of writing generic code, like because they may not understand it. I don't know which cause is true here, or maybe it's something entirely else, entirely different. But we have this problem, right? And it's really good to have identical interfaces, unified interfaces between types that are in some way similar. Sometimes we may not see that similarity when writing code for the first time, but at some point we will notice that there are some common operations we can do on different types, like future and optional. And the good thing here would be to unify the interfaces. And of course, we can do that locally in a library that will use those types. But then again, for every such library, there will be wrappers around function calls, which will be redundant, and they will all sit in the same place instead of sitting where the type is defined, which would be beneficial from the code structure point of view, even if not from any else point of view. And a slight digression. So portability. So they are like, they seem to be like two understandings of the word in the programming world. One means that, okay, we write code, we assume that the platform we are writing the code for is compliant with some standards, and we not care about the platform at all. And there's a different understanding. People tend to use the word portability to describe this. Oh, so we have these defined methods to port a piece of code to a new platform. So we know how to do that. We know how to deal with incompatibilities. We will slap some if-defs here, if-defs there, and everything will be good. And in the first case, we can just build it, right? Just compile, link, and be happy. In the second case, like everyone here used configure at least once in their life, right? It speeds tons of information of what it is checking. It's checking what's the size of this integer type. Why would you do that? We have, since 1999, we have a header that gives us well-defined integer types of sizes that we may want. Why would we check if int is 16 bits or 32 bits? That makes no sense. And something similar happens when people talk about writing generic code. Some people want to just write a template that will either use a concept or be it explicit concept with either enable, if, and type traits, or with concept slides that are incoming, or an implicit one, so just rely on the fact that if we have these functions available, our function will compile. And there are people who like look at code and say, okay, my code will be generic, I will specialize my function for this type, this type, this type, and this type, and I will be generic. That's not really the case, not really the point. So we want to write code that will behave similarly or in the same way for types that are similar. And of course, again, do not force any interfaces on here. Some people like to make singletons out of everything that they think will never be used more than one at once in a program. And that's forcing a pattern. And we do not want to do that. Sometimes code will have just one use. Sometimes there is no possibility to reuse a piece of code, or to say, okay, there may be some other data type that is similar to our data type, and that is fine. And as I said, there are types called abstract singleton factory out there. Sometimes you can find a type where there is bin at the end. This has gone too far. We want to be generic, but once we are too generic, we start having problems. And sometimes you will write a type, and after some time, you will look at it and say, oh, hey, this fulfills this concept I didn't think about when I wrote this type. And I have a use case for that. And instead of trying to create a library of wrappers or of additional utility functions somewhere else, far away from the type, try to add functionalities to the type, be it using member functions or better using free functions, or better yet, free pure functions. Okay, so we would like to design code for the successful cases. And this is basically the same principle that says that our code should not be full of try-catch blocks. We should just assume that it works. We write code where we do not check for errors, and we only check for them when we actually want to handle them. So primarily, the primary goal is to write an interface for the situation where something we expected happened. There was no problem. And you want to, of course, handle the problematic situations, but please do not design your interfaces thinking primarily of them. There is one such case currently being, let's say, processed by the committee, and it's standard future.den. So basically, to summarize the big quote from the proposal up there, we do not have a single base class for every exception in C++. So that means we cannot take the approach of passing the exception by value to a continuation for the error nose case. So we will just pass a future to .den, and then people can rethrow it by calling .get on the future inside the continuation. So I don't believe this really makes sense, because suddenly we have a function, a continuation for the future, and we want it to be called to continue the work that was done before. And we really care about the value, not about the future itself. And you can pass you could pass like exception pointer, the standard type exception pointer, to the continuation in case where we want to handle the error. If you don't know it, you can call rethrow exception with exception pointer, and then the original exception will be thrown in a given context. So this gives us basically the same way of handling the exception inside the continuation as passing a future into it. Because if we get a future, we have to call .get, and we get the exception thrown the same way. But we do not have to write this line in every continuation we have. Because this is basically what we will have to do. We will have to extract the value from the future every time and every time. And the exception will be rethrown for every one of those. So if we have 5 continuations attached and only the last one handles the error, we will have the exception rethrown 5 times. instead of having it rethrown just once, for example, by standard rethrow exception. And so this doesn't solve the case of exceptions that are not derived from standard exception, but will, in all cases with such exceptions, if we are not expecting them, we will also have to write catch ... to catch them and do something with it. We do not like this case, but it is not different for futures than it is for regular exceptions. And all this doesn't matter when the functions are not throwing exceptions. So in the successful case, we kind of pay the price of the case where the exception wasn't thrown. So I believe this is not a correct way to design an interface. So the guideline here would be try to think about successful cases, primarily write interfaces that will work for them, and then if you cannot find a way to handle errors with interface designed in this way, try to find another one, but again with the same guideline. And I like designing interfaces by first writing the uses of them. Usually my use will assume that nothing bad happened, or I will just catch everything and log the situation. So when it actually happens, I know what happened. And not having to care about erroneous cases when prototyping, for example. A prototype can very well become the final interface if we find that it works well. So we don't really want to care about errors at all stages of writing code, of creating an interface. Okay, so again about writing generic code, because I believe this is one of the more important things to talk about. And we want to see patterns. We some types have common operations. That's a pattern. And people tend to look at the known patterns, the patterns they've been taught, the patterns they did not observe themselves, and try to say, okay, so this will definitely be a singleton, without thinking about possible uses of the interface other than their primary one. And we do not design interfaces, because when we try to design an interface, I have this bright idea, I will write it down, then I will implement it. That doesn't work. That's how all the high-level design documents look like, the ones that are shown to the management to say, this is a great system, this will work, we didn't even try to implement it, but this will work. So the most useful patterns and abstractions you will come across, you will notice them because you've written the same code in multiple places. And your brain will be like, okay, I wrote this before, this might be a useful abstraction. But if you will try to say, okay, this will definitely be a useful abstraction, and it will not. You will use it once, twice, but not many more times. And oftentimes, those abstractions will be quite generic. And they will often be algorithms that operate on a data structure that follows an interface and will do something with them in a generic way, often by passing a function to them, a callback, whatever. So this gives us higher order functions, so functions which take other functions as arguments. And of course we saw that in C++, that was seen, that was noticed, and we got STL algorithms. And in C++11 it of course got easier with lambdas, and even easier in 14 with generic lambdas. We knew this for a long time. And then somebody said, okay, so this is like a function, but so this looks like a function, so maybe it's a functor. It's a nice word, I think I will use it. So this is kind of an example of trying to make a, let's say, interface. So we say it's a functor, but different people will see different abstractions when they hear the word functor. Functional programmers will see a term from the category theory. C++ programmers will see what is basically a function object. So this is a case of a name clash. We do not want that. We want, when trying to write an interface, we want to think about function names as much as we think about the actual code we write. Because sometimes a type will accidentally fulfill a concept, and code that should not compile will compile without us wanting to. So be careful. Okay, so to kind of summarize the guidelines, which are not absolute, which are meant to be broken when it makes sense. Do not follow guidelines blindly. This is also a guideline. Breaking a guideline is completely fine, as long as we know what we are doing. And a good sign to know whether we should break a guideline is if we are heavily thinking about breaking it. So in many cases, when people are sure, okay, so this is one of those places. This is one of those places where I want to break a guideline. I'm sure about it. It usually is not one of those places. Okay, so immutable data is always fine to share around, or almost always. Mutable data is fine as long as it's not owned by different scopes. So as long as it stays in a single scope, it's pretty much always fine, and there isn't really anything that can go wrong about it. Explicit flow of data is easier to reason about. When we see all the inputs and all the outputs of a function in code written explicitly, we see what is going on. If there are some magic inputs, implicit inputs hidden somewhere in the implementation of a function, it's harder to determine what is really happening, what is going on. And abstractions are discovered, and it's an iterative process. So we will not see them immediately. We will go through different versions of an abstraction. That is fine. Just do not artificially create abstractions because you think they will work, because they won't. Okay, so that's it from me. Okay, any questions?
You need a microphone?
No, that's okay. Yeah, you'd mentioned in one of the slides about with the immutable data types, how that they could be, I guess, implemented with nodes, but still be memory efficient. Like, could you go into that a little bit, like how you have?
What I meant was memory efficient in the. Okay, so the question was. What I really meant by the memory efficiency of immutable data structures, I meant memory usage. So not like the performance, which as I said, I explicitly did not talk about, but when you have shared nodes between multiple instances of the same data structure, you will use less memory. That was my point.
So the nodes that appear in one immutable collection would be referenced, or like the same nodes appear in the other immutable collection.
Yes.
Okay.
So the clarification was there will be some nodes that appear in two collections. Yes, there will. Because, for example, with a function, probably the most frequently mentioned functional data structure is a list. So when you have a list, an instance of a list, you can create a node, a new node, that says, okay, so the next node is over there. You can point the new node into the old list. So by pointing into the new node, you will point to a new instance. By pointing to the first one of the original one, you will have the original instance of the data structure.
So you said that by passing immutable data structures to other threads, you can help, with you don't have to worry about mutability between threads. But are you not just getting rid of things like torn reads and torn writes and creating a new problem where you've got stale data sitting in old threads?
Okay, so the comment was that if we are passing immutable data this way, we will have stale data. So, of course, this approach doesn't really work for types where we want to modify data. So the case you are talking about, we have stale data here. It's because we modified something conceptually. We didn't actually modify bytes that represent it, but we have a new data structure with new value. So of course you cannot use a functional data structure that way in this case. You would have to, you basically need, this is one of the cases where identity is important, because you want to refer always to the same data structure, not the same value of a data structure. Okay, thank you.